So we've come a long way in this unit so far. We've come all the way from talking about just the kind of numbers we're going to work with, how we operate on those numbers, combining them into expressions and equations, manipulating expressions and equations to simplify them and to solve them, forming functions, graphing functions, and looking at nonlinear functions that can describe real things. What we're going to move on to now is looking at the idea of change. And when we look at the idea of change in mathematics, that's all about using calculus. So what we're going to do in this video is just start off with a motivating problem to see why we might actually want to look at using calculus and why we can't just use other methods that are simpler and give us less information. So my motivating problem is all about the athlete Usain Bolt. Now back in 2009, Bolt set the 100-meter sprint world record at the Berlin World Championships. The International Association of Athletics Federations collected heaps of data on this, and they collect more and more data every time they run these things. So some of the data that they collected about Bolt's run in the 100 meters is shown in this little table just here. So they had that Bolt finished the 100 meters in 9.58 seconds. That's the kind of thing you usually see reported. But what they also had was split times, 10-meter intervals, and that's what's shown in the table. So you can see Bolt's time, 1.89 seconds to reach 10 meters, 2.88 seconds to reach 20 meters, and so on, all the way along until we get to 9.58 seconds for the total 100 meters of the race. So how does this motivate calculus? Well, let's first of all just look at this first piece of information, that Bolt finished the 100 meters in 9.58 seconds. That first piece of data essentially gives us two pieces of information. One that we can kind of assume is that Bolt had a starting point of 0 meters and 0 seconds. That's like the zero, the origin if you like. And his final point was 100 meters away, 9.58 seconds later. So we get two pieces of data out of that really. And I've shown that in this little graph here. So we've got time in seconds across the horizontal axis and distance in meters on the vertical axis. Starts at 0, 0, and he ends up 9.58 seconds, 100 meters away. Now what we can tell from that is an average speed. If we take the distance travelled, or 100 minus 0, and divide it by the time taken, 9.58 minus 0, we get his average speed over the whole race. And you calculate that on your calculator and get 10.44 meters per second. Now that in itself might be enough for a news report. But what about for Bolt himself, his coaches and trainers, and for his competitors? They might be thinking, how do I do better? Or how do I beat Usain Bolt? And what they're really interested in is what goes on in the middle here. They need to look at things not just over the average, over the length of the race, but over the little pieces in between the race. So they look to get more detailed information. So that takes us to the splits, the 11 points of data that you can see back in the table here, 10 of which are shown, and the 0, 0 which is assumed as the starting point. So we can plot those, and you can see those here on the red graph. You can see there's the 0, 0 point that we had in the previous figure, and the 109.58 point, and then there's all those other data points along the way. So you can see that Bolt's track, or his distance versus time graph, was not just that simple straight line that we had on the previous slide. It's this sort of curved line that sort of starts off a little bit slower and then speeds up as he gets towards the end. I wonder what would happen if it was a longer race, what sort of shape this graph might have taken. Well, that's not really for now. But what does this give us, this extra set of points of data? Well, they give us average speeds, but for more points. So we could calculate the average speed here, 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 and all the way along in these little 10-meter intervals. We'd know that the speed for the first 10 meters was fairly slow, but at the end he was really starting to speed up to his probably maximum speed over the 100 meters. So we get a bit of an idea about how Bolt is able to make this sort of race. He starts off slow and then speeds up. Now in the 100 meters, that's most likely just the nature of the way people run 100 meters. You can't really start off at the speed that he finishes at. But in other races, this kind of information can be quite useful in advising different runners on how to run the race like the best in the world. But what I'm wondering is, what happens if we had more and more data points and we got shorter and shorter pieces of average rates of change, or average speeds. What happens if we actually wanted to know not the average over a piece of, or a length of time, but at an instant in time, what was the speed? Well, that idea of moving from averages over longer periods to averages over shorter and shorter and shorter periods, approaching or limiting towards an instant in time, that's the whole idea of calculus. And that's what we're going to be looking at for the next few videos. So we say that taking the idea to its logical limit, we could obtain an instantaneous speed. If you like, that's kind of like the speed that the police might be trying to measure as they point the radar gun at you as you're driving down the freeway. Well, that idea of the instantaneous rate of change, it leads us to the mathematical concept of what we call a derivative. The derivative is the instantaneous rate of change of a function. What we're going to move on to in the next video is figuring out how we mathematically come up with a derivative, and then we'll move a bit further into figuring out how to actually calculate them, and then finally how to use them. So that's it for this video, just a bit of a motivating problem. You can jump onto the next video straight away because there's no worksheets for this one.